In previous lecture, you have discussed in very detail the partition function of a system in canonical ensemble. Now today as an example, we are taking to deal with the properties of a perfect gas in canonical ensemble. And for this you will first of all need what will be the partition function in case of the canonical ensemble is made up of perfect gas. You know, the problem of perfect gas is a very important problem, and it is variously used in statistical thermodynamics almost at all places. As you have seen this the same problem in case of microcanonical ensemble earlier, and today we will discuss the important properties like what will be the Helmholtz free energy, what will be the entropy, and what will be the internal energy of a perfect gas if this gas constitute the canonical ensemble. And for the calculation of all these properties, first of all we have to find out what will be the partition function of the canonical ensemble in case of the in case the ensemble is made up of perfect gas. So let us try to find first of all what will be the partition function of this canonical ensemble made up of perfect gas. As you have learnt in the previous lecture that the classical partition function for a canonical ensemble in general is given by this expression. Definitely you have an idea of this expression because you have learnt this expression already in the previous lecture, that it is given by z equal to 1 over n factorial times h to the power 3n integral of e to the power minus e over tau d gamma. Here you know this tau is equal to kT, where k is Boltzmann constant and T is thermodynamical temperature, and tau, which is equal to kT and which have dimension of energy, this is called a statistical temperature. All these things you know better. Okay. Now, to find the expression for this Z in case of a perfect gas, you have to think about what should be the energy of this perfect gas. As you know, perfect gas is a gas in which we neglect the intermolecular interaction. That is, we consider that the molecules of a perfect gas do not interact one another. And when there will be no mutual interaction, you know, in that condition, the potential energy of the system will be zero. On the other hand, you also know that a perfect gas is treated like a monatomic gas, and if a gas is monatomic, it has only translational degree of freedom, no rotational degree of freedom, no vibrational degree of freedom. So whenever you talk about the total energy of a perfect gas, that means you are talking about the translational kinetic energy, because translational kinetic energy of the molecules of a perfect gas will be the total energy of this gas, because its potential energy will be zero, and there will be no vibrational kinetic energy, no rotational kinetic energy, because these degrees of freedom of a perfect gas is zero since it is monatomic. Okay. So I have written here, you can see that the energy E is simply equal to translational kinetic energy. And translational kinetic energy, you know, this is simply P square over 2m. So if you consider that the ith molecule of the gas has a linear momentum pi, then its kinetic energy will be pi square divided by 2m, where m is actually the mass of a molecule and pi is momentum of the ith molecule. And whenever you sum up it, then you will get the total energy. So summation over I equal to 1 to 3n pi square over 2m. This gives the total energy of this system. Here actually this 3n represents the total degree of freedom. Total degree of freedom, because we have considered that the system consists of n molecules and each molecule will have 3 translational degree of freedom. So the total degree of freedom of one molecule will be 3, and so that the total degree of freedom of n molecules will be 3n. So the upper limit has been taken here 3n. Okay. This is the expression for the energy of this system. Now we will simply substitute this value of energy in this equation 1. Apart from that, you also note that this d gamma represents the elementary volume or the hypervolume in phase space. And this volume you have learnt earlier that this d gamma is given by product of dqi times dpi, where again I runs from 1 to 3n. Okay, you all know these expressions. Now we will substitute these two values, that is the value of energy E and this d gamma, in this equation 1 as you can see here. Okay, so let us substitute it. So after substituting these two values, we get that Z is equal to 1 over n factorial times h to the power 3n integral product of I1 to 3n e to the power minus pi square over 2m dqi times dpi. Okay. Now again you have learned earlier particularly in Bose-Einstein statistics that or in Maxwell-Boltzmann statistics, that if we consider that our system is enclosed in an enclosure in a volume V, here V is actually the geometrical volume or volume in configuration space, then this position coordinate actually gives the volume in position space, and this is given by integral I product of dqi from I1 to 3n, and that will be equal to V to the power n. Okay, you know it. So after substituting this value of integral of dqi in this equation 2, this equation 2 will become what? You can see here, this equation will be now written as z equal to V to the power n over n factorial times h to the power 3n and integral e to the power minus pi square over 2m tau tau, here I have not written tau, here there will be tau times dpi, and the limit of the integration will be what? As you know, in classical mechanics there is no limit on speed, that is no defined upper limit. We simply consider that the velocity may be infinity, and since momentum is a vector, so its value will lie from minus infinity to plus infinity. And again, since here there is a product of this factor and the limit of product runs from 1 to 3n, so you can take this 3n as a power on this integral. Okay. Now the integral inside this square bracket, this is a standard integral which is called Gaussian integral. You have definitely an idea of this Gaussian integral and you have used it various times. You know the Gaussian integral of e to the power minus ax squared dx from minus infinity to plus infinity, this is simply equal to a square root of pi over a. So comparing with this standard integral, you can easily write what will be the value of this integral running from minus infinity to plus infinity e to the power minus pi square over 2m tau dpi. Here you can compare this expression with the standard result, and you can find that actually at the place of x there is pi, okay, and at the place of constant a there is 1 over 2m tau. So using that expression you can write the value of this integral like this. This is square root of pi over 1 over 2m tau, and so this will be simply a square root of 2 pi m tau. Okay, we will substitute the value of tau equal to kt in last for calculation. This use of tau is more simpler, so I have written here tau. So after substituting the value of this integral in this equation, you can see equation number 3, what will be our result? Expression for the partition function z will be equal to 1 over n factorial times h to the power 3n times v to the power n and 2 pi m tau whole to the power 3n by 2, because here power is 1 by 2, but as this integral contains the power 3n, so the power will become 3n by 2. Now when you will substitute tau equal to kt in this expression, the expression for the partition function z will become v to the power n over n factorial times 2 pi m kt over h square whole to the power 3n by 2. Okay, you can check. So this is the expression for the partition function of a gas, of a canonical ensemble, not gas, of a canonical ensemble when the ensemble is made up of perfect gas. Okay, this is the expression. You should remember it. Okay. Now we will put this expression in a simpler form. One thing here I want to tell you that actually this partition function is also called translational partition function, because you have seen that this gas that is the perfect gas has only translational degree of freedom. So this partition function is only due to the translational motion, and so it is also called translational partition function. Now we will express this expression of partition function in terms of the well-known de Broglie wavelength. Okay, as you know, the expression for de Broglie wavelength lambda is equal to what? This lambda is equal to h over a square root of 2 pi m kt. You have used this expression earlier too. Here h is Planck's constant, as you know. So if we will write the expression for partition function defined in this equation A1 in terms of lambda, you can see what will be your result. This result will be simply like this: z equal to 1 over n factorial times v over lambda cube to the power n. And this result can be written like this: z equal to f to the power n over n factorial. Here actually we have written f instead of v over lambda cube. And when you will substitute the value of lambda cube here, then the value of f will be what? This will be v times 3/2 power of 2 pi m kt over h square. Okay. Now you can see what is this f? F is actually partition function per particle or per molecule, because if you consider that there is only one molecule, then n will be equal to 1, and if n is 1, then you will see that z will be equal to f. So substituting n equal to 1 in that expression, you can see z will be equal to f over 1 factorial, and 1 factorial is 1, so this is simply equal to f. So you can define this f, which we have substituted here, as a partition function of one particle. So f is simply the one particle partition function, you can say. So I hope you have understand what will be the expression for the partition function of canonical ensemble in case of the ensemble is made up of perfect gas. And you should remember this expression too. This expression is most in simpler form, and for this you have to remember this expression for the f. Okay. Now using this expression of partition function, we will be able to find out the expression for the different thermodynamic properties of the perfect gas. Actually, here in this lecture, I have calculated the three important properties of perfect gas. First one is Helmholtz free energy, as you can see here. Second will be entropy, and the third will be internal energy. So the lecture will be somewhat longer, but I hope you will watch the lecture, watch the video till the end. Okay. So if you want to find the expression for Helmholtz free energy for a perfect gas constituting the canonical ensemble, you should remember what is the general expression for this Helmholtz free energy in terms of partition function. I have already discussed these things in earlier lectures, so you can remember it. As you know, the Helmholtz free energy in terms of partition function is given like this. F is equal to minus kT ln z, log of z. Okay, and we have already calculated z here, so let us substitute the value of z in this expression, and you can see f will be equal to minus kT times log f to the power n over n factorial, because z, you have seen that z is equal to f to the power n over n factorial, as we have seen in this equation A2. Okay, so I have substituted it. Now you know that this log f to the power n over n factorial, this is what? This will be simply n log f minus log n factorial. Okay. Now this log n factorial, it is a well-known term, and it is simplified in terms of Stirling approximation. And you know, according to Stirling approximation, log n factorial is equal to n log n minus n. So at the place of this log n factorial, now let us substitute this expression n log n minus n. And after substituting, we will get the value of f. So f will be now equal to what? This will be minus kT times n log f minus n log n plus n. Okay. Now you can take this n as a common factor, and inside the square bracket there will be log f minus log n plus 1. But log f minus log n, you know, this is log f by n. So the expression for the Helmholtz free energy f you get is minus n kT log f by n plus 1. Okay. This is the standard result, and you should remember it too. Now, when we will substitute the value of f, which we have already defined earlier, you can see here in this equation 5. So after substituting the value of f, you can write that f is equal to minus n kT times log v by n times 2 pi m kT over h square whole to the power 3 by 2 plus 1. And you can see this is the expression for the Helmholtz free energy. And from this equation, you can easily recognize that this Helmholtz free energy actually depends on, importantly, on two factors. The first one is the temperature T, and the another is volume V. You can see it here. So T and V affects the value of this Helmholtz free energy. Apart from this, it also depends on the number of molecules, that is mass of the gas. But if we are talking about a gas of given mass, then n will be constant, but due to the variation of temperature and volume, this Helmholtz free energy will vary. Okay. Now we will calculate the another most important property of this perfect gas, and this is its entropy. You know, entropy is a most important thermodynamical property of any thermodynamic system. So again, I will say you that for finding the expression for entropy, you must remember what you have learned earlier. The expression for entropy in general for in terms of in terms of Helmholtz free energy. You know, in terms of Helmholtz free energy, entropy of a system S is defined like this. This is minus partial derivative of Helmholtz free energy F with respect to temperature at constant volume. Okay, this should be constant because you know F also depends on V. So here if you are differentiating this F with respect to T, you must keep this volume constant. Although I have used the symbol of partial differentiation, so there is no need to write this constant V, because when you will differentiate partially with respect to T, V will be constant. Okay. Now to find the expression for S, we will have to substitute the value of F which we have obtained here in this equation A3. So let us substitute the value of F defined in equation A3 in this result and simplify it. Then you will get the entropy of the system. Okay. So let us put, you can see the expression. This is your expression, F equal to minus nkt log F by n plus 1. So after substituting this, S will be what? This will be minus del T operated on minus nkt ln f of n, F by n minus nkt at constant volume. Okay. But there is no need to write this V because we are differentiating partially. Now we will operate this operator separately on the two terms inside this square bracket. But see the first term. The first term is nkt log F by n. Here actually this is a product of two functions. T is a variable and F is also a variable. So we will use the rule of differentiation of product of two functions. So keeping this log F by n constant, our result will be what? Since there is minus sign, so all these minus will become plus. So this will be nk log F by n. Here T has been differentiated and you know this del T by del T will be equal to 1. Okay. Now we will keep T constant and we will differentiate log F by n. So the second term is nkt del T operated on log F by n. And when you will operate this operator on the last term, that is nkt, this del T by del T will be 1. So the last term will remain simply nk. Okay. Now let us simplify this result to some extent. You can see the first term is nk log F by n and the second term is nkt del T operated on this log F by n. But now substitute the value of F. After substituting the value of F, you will see the expression inside the bracket will be what? This will be log V by n times 2 pi mkt over h square whole to the power 3 by 2 plus nk. Okay. And this will be nk log F by n times, plus nkt. Now log V by n times 2 pi mkt whole to the power 3 by 2. This will be differentiated with respect to T, keeping V constant. So what will be the result? First of all, this log V by n times 2 pi mkt whole to the power 3 by 2 by h square, that will be differentiated with respect to V by n times 2 pi mkt over h square whole to the power 3 by 2. And that will be 1 by V by n times 2 pi mkt over h square whole to the power 3 by 2. Now this factor V by n times 2 pi mkt whole to the power whole divided by h square whole to the power 3 by 2. This will be now differentiated. Since V by n times 2 pi mk over h square to the power 3 by 2, this is a constant factor. So this is outside of the differential. And this t to the power 3 by 2, this will be differentiated. And that will be simply 3 by 2 into t to the power half. And the remaining term is plus nk. Okay. Now you can see this V by N 2 pi m kt whole to the power 3 by 2 by h square. This will cancel out by this. This t and this t square, t to the power half, this will be t to the power 3 by 2. So all these factors will cancel out. And in the second term only remains 3 by 2 times nk. So your result is nk times log f by n plus 3 by 2 nk plus nk. And this 3 by 2 nk plus nk, you know, this is 5 by 2 nk. So expression for entropy will be what? This will be nk log f by n plus 5 by 2 nk. I have written it here, you can see. And now again we will substitute the value of f. After substituting the value of f, you can see s will be equal to nk times log v over n times 2 pi m kt over h square whole to the power 3 by 2 plus 5 by 2 nk. After seeing this final result, can you remember this result you have already studied earlier? Definitely you can remember. When we have discussed the Sackur-Tetrode equation in previous lecture in microcanonical ensemble, then we have seen this result. This expression of entropy of a perfect gas is a correct expression because it follows the additive properties of the entropy, and you know this is well known Sackur-Tetrode equation. And exactly the same result you have obtained in case of a microcanonical ensemble when the ensemble was made up of perfect gas. So you can be surprised that our ensemble has been changed, but result for entropy is same. So if you calculate the entropy of a perfect gas when the perfect gas constitute a microcanonical ensemble, and if you calculate the entropy of a perfect gas when it constitutes a canonical ensemble, result will be same. And that result is simply called Sackur-Tetrode equation. This is a very remarkable result that in calculation of entropy, the result is same in case of both microcanonical ensemble and canonical ensemble. There is no difference. So actually this result validates or verifies the fact that entropy is determined by energy independently of whether the system is isolated or in thermal contact of heat reservoir. You know, in case of microcanonical ensemble, the energy remains constant, that is the system is isolated. But in case of canonical ensemble, you know energy varies because our system in this case is in thermal contact of a heat reservoir. So here temperature remains constant. But it does not matter that energy varies or energy remains constant. An expression for entropy will be same. So it does not matter that whether you are considering that energy is constant or energy is variable, energy is varying. It does not matter in calculation of entropy of a perfect gas. Okay. So this is a very remarkable fact. Now we will see the calculation of the third and the last important property of our perfect gas, and this is regarding the internal energy of this gas. Okay. For calculating this internal energy, we will actually calculate the average translational kinetic energy of this gas at a given temperature T. That will be actually called the internal energy, because in case of ideal gas or perfect gas, you know, the energy is only in the form of translational kinetic energy. Okay. And for calculating this, you have to assume an energy state, which I have assumed here, ith energy state. And as you know, an energy state, ith energy state, which has energy eigenvalue Ei, that may be a degenerate energy eigenvalue or maybe non-degenerate. If we consider that this ith energy state or this ith energy eigenvalue Ei is non-degenerate, it means corresponding to this energy eigenvalue, the degeneracy is 1, or there is only one quantum state. But if you will consider that this energy eigenvalue is degenerate and its degeneracy is Gn, then the system will have Gn quantum states corresponding to this energy state. But for simplicity, I have considered here that this ith energy state is non-degenerate. Okay? So the degeneracy of this eigenvalue Ei will be 1. And in this condition, if you want to find the average energy or the mean energy of this system, what will be the value? You know, the average energy, which has been written here by E inside this angular bracket, this will be defined as summation over I Ei e to the power Ei by kt divided by summation over I e to the power minus Ei by kt. You know it. Okay? But you have already discussed the partition function of a canonical ensemble, particularly the quantum expression for partition function. You know, the quantum partition function of a canonical ensemble is given by z equal to summation over I e to the power minus Ei by kt. Okay? Now actually we have to use this result in this equation 1, and for this we will need some mathematical steps. So for this, let us take the natural log of this expression. So because we are actually transforming this result in terms of what? In terms of Helmholtz free energy. And in Helmholtz free energy, the log comes. So I have taken here this log. Log z will be equal to what? This will be log of summation over I e to the power minus Ei by kt. Okay? Now let us differentiate it partially with respect to temperature T. So del T ln z. This will be what? You have to differentiate it with respect to T partially. And you know from the rules of differentiation, this will be simply 1 over summation over e to the power minus Ei by kt, okay, times. Now this summation over I e to the power minus Ei by kt will be differentiated. So when this will be differentiated with respect to minus Ei by kt, then this will be same, that is summation e to the power minus Ei by kt. Now this minus Ei by kt will be differentiated. So minus Ei by k is a constant factor, and derivative of 1 over t, that will be minus 1 over t square. So now this minus and minus will become plus, okay, and what will be the expression in RHS, you can see, and this kt square when multiplied in LHS, this will be kt square times del t log z, and that will be equal to summation over I Ei e to the power minus Ei by kt over summation over I e to the power minus Ei by kt. Okay? But you can see the RHS of this expression represents what? This is simply the average energy E. Okay? So I have written here the average value of energy E. Okay? And so you can say that the average energy E is simply equal to kt square times partial derivative of log z with respect to t. Okay? But you have learnt earlier, just now, that the Helmholtz free energy F is given by minus kt ln z. So log of z, this will be equal to minus f by kt. So now use this expression of log z in this equation number 2 at the place of log z. So after substituting this value, you can see the average energy will be equal to minus kt square del t and f over kt. Okay? Now, you have seen this equation A3 here. See the equation A3. This is your equation A3. The value of f is this much. So now we will use this value of f which we have derived earlier in this expression at the place of f, and then we will actually differentiate it. So you can see after I have written already that expression here. F is equal to minus nkt log f by n minus nkt. So let us substitute that value of f here. So after substituting that value in this expression, you can see our result will be what? This result will be E equal to kt square del t n log f by n plus n. Okay. Now this is n can be taken as a common factor, and so this will be n kt square del t log f by n, because here there will be 1 and derivative of 1 will be 0. Okay. Now for differentiating it, we will have to substitute the actual value of this small f, which is partition function per particle. So after substituting the value of a small f, our expression will be what? This will be n kt square del t ln v by n times 2 pi mkt whole to the power 2 pi mkt over h square whole to the power 3 by 2. Now we will differentiate this expression, and you know after differentiation what you will get. This will be 1 over v by n times 2 pi mkt over h square whole to the power 3 by 2. Now this will be differentiated, this denominator will be differentiated with respect to t, and in this v by n times 2 pi mk over h square whole to the power 3 by 2, this is a constant factor. So this has been taken outside, and differentiation will be of t to the power 3 by 2. That will be 3 by 2 times t to the power half. Okay. Now you can see this v by n 2 pi mk h square whole to the power 3 by 2, and this will cancel out. Now in numerator there is t square times t to the power half, and in denominator there is t to the power 3 by 2. So you can see this will be equal to t. Okay, and so your expression for E will be equal to what? This will be 3 by 2 nkt. So this is the mean value or average value of the system of a perfect gas. Okay, and as I have told you earlier that in a perfect gas the energy is only in the form of this translational kinetic energy. So this average energy actually represents the total internal energy of the perfect gas. So if you denote the internal energy of perfect gas by the symbol U, that U will be equal to this average value of E, and that is equal to 3 by 2 nkt. And this is also a well-known result. Even in Maxwell-Boltzmann statistics you have seen this. In microcanonical ensemble you have seen this. Okay, so you can see this ensemble concept is only the different approach. It does not gives any new thing. It is different approach, because this result is same as we have obtained in case of microcanonical ensemble. So sometimes a question will be asked to you that so that the three ensembles give the same result or agree with one another. So these are the examples, or these are the proofs you can say that which actually proves that the ensembles are only different approaches, they do not give different results. Okay, so I hope you have clearly understand the concept dealt in this lecture, and definitely you should watch the complete video, because after watching the whole video, complete video, you get the whole concept. Thank you very much.